So we'll continue study how to draw the graph. Okay. Sometimes we have to start. You have to draw the asymptotes because the graph must be the group graph. Okay. So you have to. You cannot draw the whole graph on the screen. You only draw the local graph, but nearby infinity, you have to tell me how does it look like. Describe it. So my first function. This is a typical function. Okay. F of x equals x squared root of 1 minus x. Okay. You're given this function and sketch the graph of y equals f of x. First thing you have to do is to find the domain. Where's the function is defined? And look at the square root of 6 minus x, right? The domain, you have to say 6 minus x is greater than or equal to 0, x is less than or equal to 6. So graph is only defined on the left-hand side of 6. Okay? So the domain is going to be from -infinity to 6. Before you find the derivative, what information you have to get? You should know where the graph is above the axis, where the graph is below the axis, right? And where the intercepts. So intercepts is also, intercepts. Then you can get the graph right away, okay? Intercepts to say clearly when the y-intercept is let x to be 0, then the y is going to be 0, okay? But you also have to try to solve this equation. Then you get the x-intercepts. X-intercepts, x equals 0, but the x is also equal to 6. So the graph passes through, this is a y and this is 6. The graph passing through those 2 points. Okay, it's only defined on the left-hand side of 6. All right, then I have to decide whether the graph is above the axis or below the axis, right? Yeah, above the axis or below the axis. So you have to quickly make a decision. And then look at the function. Square root of x, 6 minus x will never be negative. Right? So the sign is completely determines the sign of x. So clearly, f of x, the sign. Okay, so f of x is positive for x between 0 and 6. F of x is negative for x less than 0. Okay, so that means the graph is here below the axis, and so I've got the graph already, right? So we have the graph. What we needed to know is the asymptotic behavior of x of the graph as x approaches negative infinity. I also want to know the absolute maximum value. Okay, there's absolute maximum value clearly somewhere. Right. So maybe the function, concave up somewhere, but at least there's some areas concave down, right? Between 0 and the S6 is concave down. Even beyond that, maybe everywhere is concave down. So I needed to find the derivative to get the exact location of absolute maximum value, okay, or absolute local maximum value, either way. So now it's time to sketch this graph, okay? But probably needed to know the asymptotic behavior of the function. Okay, this will be the asymptotic. Okay, as x goes to negative infinity, I'm going to look at the function. Here's x 6 minus x, right? I take x out, but this will be the negative x because the positive x. This will be positive, right? So it's going to be it is going to be 1 over 6 minus x. I think so. Yeah, when you multiply this out, you get it. Okay, So you will get x squared with this. And the second part is almost equal to 1. So this will be something like that. The reason I want to put a negative x is because x is negative. All right. So this is actually a negative absolute value of x. Then have a be careful about this. Yeah, the first one is this. Second one is this, right? Right? Because when x is negative, x is going to be negative absolute of x. So and let's continue. Okay. So if you want to find the asymptote, this is not be a straight line, it's a big curve. Okay. So the graph of this, look at the graph. How does the graph look like when x is negative? When x is negative, I think the graph looks like that. Okay. The graph looks like that. Okay. And the other side, because it's absolute value, so we only consider when x is negative. Okay. That's it. So if you go back to the picture, go back to the picture. Here's a 6, here's 0. I think the graph looks like that. Okay, not going to concave up. Okay, I'm pretty sure. Okay, and another, it's asymptote is not going to be horizontal. It's asymptote is going to be like that. Okay, y equals negative x to the 3/2. They're getting close. Okay. It's rough estimate. Okay. All right, so now we are ready to find the derivative. The asymptote is not necessarily horizontal. Could be x squared. Just look at, just simplify the function when x sufficient large. Let's find the first derivative. I'm pretty sure there's one critical number. Okay, it is going to be the derivative of, so the function itself is going to be x, 6 minus x to the 1/2. So let's differentiate. 1 product rule, right? And x times the 1/2, 6 minus x to the negative 1/2, negative 1. Okay, great. How do I solve it? Okay, I have to take this part out. Okay, I take this part out. Then this side will be just this. And here I got minus a minus, right? Minus half of x. Okay. All right. So let's simplify it. You will get 6 minus 3/2x. Okay. You can also take 3/2 out. Then we and take negative 3 out, right? So you will get 4 minus x. Yes. No, it's the same question. I haven't completed the graph yet. I needed to know before I find the derivative. Already get the graph. Okay, I'm trying to get a sketch graph without finding the derivative. Okay, so the first part is just determine the two zeros. X-intercepts, and then I needed to know how does this, okay, which way it's going. Okay, so I have to find the asymptote for that curve. So I when x sufficient large, I drop the rest of the part. I end up with this function. Okay, and this part can be dropped. Okay, and then I draw this graph. It's the power is 3/2, so it's larger than 1, so it should be concave down. Okay, so this is a graph. So the curve in the red color. So this is the asymptote. So the graph of the function will be very close to the graph of that special curve. So this is actually this becomes a asymptote. Okay. Then I needed to know where's the maximum point, right? My guess is this is a place it's going to be 0. And here the derivative is negative. Here the derivative is positive. Maybe positive everywhere. But also I guess the second derivative should be greater than 0 everywhere. No, not greater than, less than 0. Okay. Second derivative because it can carry down. Okay. It's not clear yet until we verify using derivative. Okay. But looks like there's no inflection point, so it can carry down. So I find the first derivative. I want to set this to be 0. So what I got after simplifying, sometimes I needed to know the sign. So I find out, this part is always positive when x is less than 6. But this part, 4 minus x, can be negative, can be positive. It's possible because when x is greater than, when x is greater than 4, it's negative. So clearly, if x is less than 6, greater than 4, and this is going to be positive if x is less than 4, okay? So concave down, concave up. That's why the picture looks like that, right? Okay. So f of 4 is going to be 4 square root of 6 minus 4 square root of 2 is the absolute maximum value, not the point, value, okay? The highest point. Okay, because on the left hand side of the graph is always increasing, on the right hand side of the graph decreasing. So that's the highest point. So you get the exact location of the maximum point. All right, but we needed to know whether there's inflection points. I needed to look at second derivative. The second derivative, okay. The second derivative, a little bit complicated, right, to differentiate. So let's continue differentiate, okay. So it's a 3 over 2. The first fact is going to be negative 1/2 6 minus x to the negative 1/2 minus 1 3 over 2, but times negative 1. Okay, plus and that is going to be negative. Now we still have to simplify, right? How to simplify? You take the term with the lowest power, negative 3 over 2. So this is a common fact. So I take 3 over 2, 6 minus x to the negative 3 over 2. Then what I have here, negative 1/2 times 1 is positive 1/2. 4 minus x, okay. Then I have a negative 6 minus x. Right. So if I take 2 out, I get 4 minus x minus 2 times x, 12, plus 2x. So that is going to be that's going to be x minus 8. I should there say that this is always negative for x less than 6, because we only consider the case when x is less than 6. Okay, so x minus 8 is negative. So everywhere it matches what we show at the very beginning. So that implies the f is concave down on the interval from negative infinity to 6. Okay, so we are done with the picture. Okay, so we get a graph. Okay, the graph concave down has absolute maximum somewhere, and yeah, finally let me draw the picture. Okay, the highest point 4 square root 2, 6 0, concave down everywhere. Okay. And also important thing is this may be approach asymptote, right? Y equals -x to the 3/2. This is an asymptote. Okay. That's one. Yeah, that's perfect. Right, it's a new function. Y equals f of x, 2x squared plus x minus 1, x squared plus x minus 2. I want to sketch the graph. This is a rational function. Yeah, sketch the graph. Now, how to sketch the graph without finding derivatives? You have to learn this, okay? Because it's easy to make mistakes to find the derivatives. So it's better to sketch the graph first and use the graph to check whether your computation is correct or not. Okay. So how do you sketch the graph without finding the derivative? All right, we sketch the local graph and put together. Well, first of all, let's see. Let me factor this out. I think this would be 2x minus 1, x plus 1, and x plus x minus 1, x plus 2. Okay. So you're not able to cancel any terms. But we do have some troubles when x equals 1 and x equals -2. So that gives you the vertical asymptotes. But first of all, let's find out the domain, right? The function is not defined when x equals 1, when x equals -2. So it's not defined at those 2 points. Okay. That gives you the vertical asymptotes. Second, intercepts. Y-intercept is the value when x equals 0, and that is going to be 1/2. Why? Because when you plug 0 for x, you get 1/2, -1 over -2. Okay, so then the x-intercept, x minus 1 times x plus 1, 0, so x equals 1/2, x equals -1. Okay. And we also have a horizontal asymptote, the function when x, yeah. Horizontal, yeah, asymptotes. Let's find asymptotes. Otherwise, we cannot draw the graph. Okay, so let's try to draw the graph. Okay, when x equals 1, this 1 to -2, the function is not defined at those 2 points. No graph at those 2 points. All right, x-intercept when x equals 0, y is here, and y-intercept, x-intercept when x equals 1/2, and x equals -. So the graph passing through those 2 points. Oh my God! All right, so it's hard to draw, right? But we know this. Wait a minute. We know this. So we know the function is not defined when x equals -2 and when x equals 1. Okay, because this domain does not include this 2 point. Okay, so let's look at the asymptotes. Vertical asymptotes. Okay, vertical asymptotes is when x equals 1. When x equals 1 or when x equals -2. The two vertical lines. Okay. Then horizontal. Then the horizontal asymptote. So we needed to find the limit as x. Yeah, this is a function, right? 2x squared plus x minus 1, x squared plus x minus 2. So when x sufficient large, you take 2x out, right? 2x out, then you get 1 plus 1 over 2x minus 2x squared. And you also have x out, 1 plus 1 over x minus 2 over x squared. Okay, so this 2 canceled out, and this is about equal to as x approach sufficient large, right? Because 1 over 2x is going to be 0, approach 0. So those parts can be simplified. Okay, so that means the horizontal asymptote y equals 2. Okay, and I already show you that proof. All right. So now I think we can draw the graph. Okay. We use the asymptotes using the vertical asymptote, use the x-intercept, y-intercept, we can sketch the graph. Okay. All right, so let's see. This is a -1. This is a negative asymptote, right? So near by x -2, nearby this asymptotes. Y is going to be, we look at the fact, right? X plus 2, x minus 1, and 2x minus 1, and the x plus 1, right? What we need is just the x plus 2 term. And the rest of them we can put together. Okay, this part is almost to be constant. Okay, this part is almost to be constant. So what is the value of this part? Okay, when x equals -2. When x equals -2 would be -4 minus 1, -3, and -2, so -3, right? No, this is -2 plus 1 is -1. Okay, -3 minus 1, yeah. So negative become, yeah, this is still negative. Okay, this is going to be -5/3 when x close to -2. All right, so what does that mean? So this is going to be 5/3 x plus 2. If you want to draw the graph of that simplified function, how does it look like? And this is going to be -2, right? So the graph looks like that. Okay. This is a graph y equals negative 5 over 2, x plus 2, 1 over x plus 2. Okay. Then I want to draw the graph when x equals nearby x equals what? X equals 1. If x equals 1, you have to switch the order. X minus 1 here, x plus 2, 2x minus 1, x plus 1. Okay? This part is almost equal to, that's 1. So 2 times 1 minus 1 is 1. 1 minus is 2 and 3. Okay, it's positive number. Okay, so this is going to be 2 over 3 x minus 1. Okay, if you want to draw the graph of this function, it goes like that. All right. Okay. So now I'm going to put 2 local pictures into 1. Now I can sketch the graph. Let's go back here. It's going to be 1, negative 2. Okay. So it says that the graph looks like, yeah, right? And from the picture here, I got this. Okay. So it looks like we are going to get the graph. Okay. 2 local picture I already got. I also know the intersection points. This one and that one and this one, right? So that means I needed to make sure the graph going through. Okay, there's 2 points. Okay, it's going to be negative 1, 1/2. I'm pretty sure it's 1/2 also. All right. So how about the other 2 pieces? We know the horizontal asymptote is here, right? Y equals 2. So how can you draw the other 2 pieces? Must be like that. Okay. It's, yeah. So that is the curve in the red one. I just at the very beginning, I just guess, you know. Okay. The real, yeah. But there's still question whether the curve is above the horizontal line or maybe it's across the horizontal line. Y equals 2. Okay. So we can try to see. Okay. It takes difference. F of x minus 2. Do you think it's always positive or always negative, right? So when you take this, here's x squared plus x minus 2, 2x squared plus x minus 1 minus 2. So let's simplify it. I find out 3 minus x. Okay. Okay, now question is whether this is positive or negative, right? It's also determined, it's determined by the sign in the denominator. Okay. So this is x plus 2, x minus 1. Can we determine the sign if x greater than 1 when all the x less than negative 2? Because I care about those 2 pieces. Okay, when x greater than 1, when x less than -2, it's negative, negative, positive. I think this is also positive. But here's still a question. Okay, it's not necessarily always positive, always negative. Because when x equals 3, it's going to be 0. So there's an additional point here. 1, 2, 3. Okay, somewhere here. So it's possible that okay. Oops. Okay, so it's possible. It's yeah. The difference negative. Okay, but on the left hand side it's positive. It's above the horizontal line. But here it's possible. If it's negative, that means go below the horizontal asymptote. Okay. But for x between -2 and the +1, for x between -2 and the +1, the numerator is positive, so denominator is negative. So that's why f of x is smaller than 2. Okay. So this is a sign, and I'm pretty sure this is correct picture right now. It will cross the graph will pass through the horizontal asymptote. But when x approaches infinity, positive infinity, it will go up. If that is the case, I'm going to have two critical points. Okay. Also, I can tell that, yeah, this side, and also I'm going to have an inflection point because this will go in like this, right? So and then you use the derivative to determine everything. Okay. So from the picture, I can tell. I already sketched graph. I have one local maximum point, one local minimum point. The local minimum point, local minimum value could be larger than local maximum value. Okay. I probably have one inflection point. Inflection point. Okay. This is a local minimum point. This will be the local maximum point. Okay. Point means a point. So let's find out this information. All right, we have to find the derivative. Let's find the derivative. If I find the derivative, I'm going to find the 2 zeros. Okay, so find the derivative. Well, the function is going to be complicated. Okay, what is the function again? There's the function here, over here. So find the derivative, x squared plus x minus 2 squared. Then you differentiate 4x plus 1, x squared plus x minus 2, and here 2x squared plus x minus 1, 2x plus 1. Okay? Then carefully check. Okay? Simplify the numerator. Now, if you know the graph, you can figure out the mistakes. Okay? So the numerator will be x squared minus 6x minus 1. That does not look good. Okay? But then you will get two solutions. If you set this to be 0, the numerator will be, use a quadratic formula. X is going to be plus minus okay. Here's 40 over 2. Okay, and after simplify, it's going to be square root 10. All right, so you're getting 2 critical values corresponding to local maximum, local minimum point. So let's go back to check when number is positive, other one is negative, okay? Because square root of 10 is larger than 3. So the one number is positive, okay? Other number is going to be negative, slightly negative. So I look back to my picture, I find out that it matches. I'm fine, okay? It's not only this is greater than 6, actually. Yeah, square root 10 is greater than 3. Less than 7, okay? X1 is greater than 6, less than 7. Okay, let's go back to the picture. Should be greater than 6. Where is 6? Somewhere here. Okay, the corresponding number will be 3 plus square root 10. This number will be 3 minus square root 10. Yeah, that matches the graph. Okay. So you can tell the local minimum value. Okay, and local maximum value is going to be this. And then we have to do the calculation. You can estimate. Then we have to look at second derivative. Second derivative is more complicated, and I'm pretty sure there's one point, inflection point there, somewhere. Okay, so second derivative, after computed, I got negative 2x2 plus 18x squared. It's harder to get. Okay, so this is I'm pretty sure there's one point. The second derivative changes signs. Okay, and if you set it's quadratic, it's numerator is polynomial degree 3. Okay, this one has 1, 0 on the interval. I can be sure the interval is from the lowest point somewhere here. Okay, yeah, look at the graph. Okay, we already sketched the graph. We just want to know where's the inflection point. Okay, inflection point is harder to determine right now. The value is exactly x coordinate and y coordinate. We only know this has a zeros. Okay, it's harder to solve it. Yeah, the you can try some integers. This should be larger than this should be larger than you see inflection point is here, larger than the local minimum point. Yeah, on the right side of the local minimum point, 3 times square root 10. Okay, it's not easy to find the zeros of this function, but we can try 7 or 8, some numbers like that. Okay, I will not continue, but as you see, I show you, yeah, in many cases you can solve for the zeros of the second derivative. Okay, so look at this picture. The idea is as follows: we draw the asymptotes, we draw a local picture nearby asymptotes, and we group them together. Okay, then you can tell how many local maximum values, local minimum values, right? And then use the first derivative, second derivative to get the exact location of this point. All right. Let's go back to the polynomial, rational functions, right? Then, quite radical functions. Well, now we go back to the polynomial. Look at this polynomial. This polynomial degree 3, and the leading term is x cubed. So I'm pretty sure the graph looks like that, and it passes through the origin. Okay. Well, it's hard to get, right? So the graph should be like that always. The question is, yeah, how to draw it, right? So I can take x out, x minus x plus 6. So the intercept, yeah, intercepts x equals 0, x equals -6. So 0 and -6. So the graph must be like that. I'm pretty sure. Okay. Looks like you only have a 2 x-intercept. Okay. The reason is, look at the function, right? This function f of x is positive if x is greater than 6, -6. Negative if x is less than -6. Okay, here x cannot be 0, otherwise it's not positive. So when x is greater than 6, the graph is always above the x-axis. Right? It touches the origin. Okay. That's all you can get without finding derivatives. The graph of polynomial degree 3 only have 2 fixed type of graphs. So from here, I just needed to find the local maximum point here, right? Find the derivative. So then the first derivative is 3x squared plus 12x, which is x3, here x plus 4. So set this to be 0, x equals 0, x equals -4. I'm not surprised, -4 is here. Okay. So f of 0, which is 0, is a local minimum value. Okay. So f of 4 this is a local maximum value. Yes. -4, yes, -4, because the function is, yeah, this is -4, okay, because x plus 4 equals 0. Yeah, that's right, you're right. Yeah, this is then I make mistakes. Yeah, it's not that big a number. You know, I will discover that later after I look at the picture. Okay, so it's going to be negative 4 plus 6 times 4 squared. I take the 4 out, take 4 plus 6, and it's 2 times 4, right? 32. 32 is a reasonable number. Okay, so this is a local maximum value of the function. I think we're almost there. One thing is left. Okay, so let's keep drawing the picture here. Okay. What is left? Well, we needed to know where the concavity changes. Okay, we want to know the concavity inflection point. Okay, we have to differentiate the function again. So set this to be 0, x equal -2. So the inflection point, yeah, f -2 is -2 cubed plus 6 times -2 squared, and -8 plus 24. So the inflection point is going to be -2 and 16. Okay, so now you get all the points, you get perfect graph. All right, let's try the number. Let's try the function, okay? We did before a couple times. Yeah, we sketched the graph. Can you sketch the graph? Okay, we did it. Let's see the calculation. All right, so how do you draw the graph? We don't want to, yeah, I can sketch the graph without finding derivative, okay? First of all, intercepts, right? Okay, so I needed to combine them. Okay, so let's see if we have a y-intercept or x-intercept, right? X squared plus, okay, it's never been negative, right? I think it's always positive, no solution. So the graph does not, yeah, intersect the x-axis. Okay, let's look at asymptotes. Okay, so this is going to be always going to be 1. So y equals 1 is a horizontal asymptote. Okay. So let's see. Now we have points. So how do we put them together, right? And I think we can together. This is the way, right? Going like this. This is the horizontal asymptote y equals 1. Okay, and then going to be like that. But there's a possibility. I show you. You can go be under the. It go up across the horizontal asymptote. Okay. So it's possible going. So let's look at the function y minus 2, y minus 1. So it's going to be 1 plus 1 of x plus 1 of x squared minus x, okay? Minus 1. So I get 1 of x plus 1 of x squared. I get x squared x plus 1. And this is clearly can be negative, can be positive. So that means this will be negative if x less than -1, positive if x greater than -1. So in other words, this function is going to be less than 1 if y is less than -1, greater than 1 if x is greater than -1. Okay. So where it is -1? -1 is here. Okay, when x is less than -1, the y value of the function is less than 1, so it's going up, going down. Okay, and on the right side of -1, it's always positive. It's always greater than 1, so it's above the horizontal subscript. So now I have a very clear picture. It must go like that. Okay, you have to go back because the asymptote y equals 1 is the horizontal asymptote. Now from this graph, what you can tell, there is only one local minimum value, which is also a local, this is absolute minimum value. And there is the inflection point where concavity changes, because this side must be concave down, then concave up. Okay, so here y prime is negative, and this is the y prime is positive, and the y prime is negative. And also y double prime is negative, y double prime is positive, and y double prime is positive. Okay, I can tell the sign of the function at the very beginning. I just needed to use a derivative to determine the absolute minimum point and also the inflection point. So I needed to find a derivative. Okay, let's find a derivative. Right, if I take x out, that'll be x plus 1. Okay, this is equal to 0 if x equals -1. That gives you the minimum. Yeah, so y value is going to be 1. Right, it's going to be 1. So local minimum value, this is. Oh, wait a minute. Minus 2 minus 2, yeah. Yeah, so it's not going to be. I'm going to check the value. It's going to be -1. It's negative 3 of, I think 3 or 4. Yes. Negative, negative, positive, negative. Let me double check. Yeah. No, it's a negative, positive, positive. It's a positive. Yeah, positive. Okay. So the local minimum value is positive. Let's go back to the picture here. It's positive. Okay. So this is going to be, this is -2. Okay. So now I'm going to find the inflection point. Okay, I needed to find second derivative. Okay. So second derivative, clearly it's a change of signs when x is going to go goes across -3. Okay, so clearly this will be negative if x is less than -3, positive if x is greater than -3. So now that's concave down, that's concave up. Okay, so look at the picture over here. Yeah, concave down, concave up. So the inflection point is when x equals -3, the y value is 1 plus -3 plus -3 square, and that's 2/3 plus 1/9. 7/9. Okay, so the inflection point is -3 and 7/9. Let's go back to the picture if this is correct. Okay, so you go back to the picture. Yes, I think it's 7/9, -3, 7/9. This should be higher than the absolute minimum point. Okay. So again, okay, what is the idea, main idea, right? Let's go back to this graphing problem. So your given function, it's essentially it's a rational function, x squared plus x plus 1 divided by x squared. Step 1, you're trying to figure out the intercept, okay? X-intercept, Y-intercept. It's easy. And a horizontal asymptote, the vertical asymptote. Okay, you will get a horizontal asymptote y equals 1, vertical asymptote is x equals 0. Then you draw the graph nearby the vertical asymptote. Okay? How do you draw it? Well, nearby the vertical asymptote, y is going to be about 1 over x squared. Okay? So you can draw that graph, y equals 1 over x squared. Then you look at the infinity. So you know that the graph is going to the graph will approach the horizontal line y equals y equals 1. Okay. Yeah. So this is a y equals 1. Yeah. Because y approaches 1. Okay. The only problem is whether the graph is always above the horizontal asymptote or below the horizontal asymptote. So I take the difference, y minus 1. But then I look at, oh, it's clear now, x less than 1, -1, it's negative. When x greater than negative, it's positive. So that there's a portion of the graph is below the horizontal asymptote. Once it's below the horizontal asymptote, it must goes like that. It will go across the horizontal asymptote, but you have to go up again because y equals -1 is the horizontal asymptote as x approaches negative infinity. So you have to go up. If you have to go up, there must be concave down. One side concave up, other side concave down. So there should be a inflection point. To find that, you just need to find the derivative, second derivative. And it's from second derivative, it's clear that when x equals -3, and you get the inflection point. Okay, you get the inflection point, and then you get a precise picture. Okay, so we have to learn how to sketch a graph at the without using derivatives. Okay, don't just find the derivative right away when you do the homework. Okay, so 2 steps: schedule graph without finding derivative, because that will help you to find mistakes honestly at the end. Okay, and do the homework. And we're going to have Friday next Monday we're going to have 2 more classes for section 7.3, like a strategy how to schedule graph. Okay? Yeah, how to schedule graph without using graphing calculator. So you can use our graphing calculator at home to check your answers. Okay, no problem. Okay, but graphing calculator will not show you step by step how to get there. Yeah, the break is very short, so there was almost no breaks. We had 4 break, and we are. If this is what I should say now. Not everybody can quickly understand how to schedule graph. So my suggestion is follow my the procedure here to schedule graph without using the derivatives, because it's easy to make a computation mistakes. Okay, that's the main reason. Okay, and find the time to do homework. Without doing homework, no matter how smart you cannot memorize all the stuff. Okay, and the more stuff you learn, and you get just have no idea how to handle it, right? So Yeah, you have to, you are taking other courses. I know you're busy. If everybody push you, okay, turn in the project, turn in the homework, okay, and